Okay, so let's look at the second part of chapter 16. Now in this section we will learn how we can add an acyl group on a benzene ring. Okay, so you guys must be familiar now what is acyl group. From the last chapter also we talk about acyl group is carbonyl group with alkyl group. Okay, so this is called Friedel-Crafts substitution. Two electrophilic substitutions are named for Charles Friedel and James Kraft together. Friedel-Crafts. How we can add an acyl group and how we can add an alkyl group on the benzene ring. Friedel-Crafts acylation places an acyl group on a benzene ring, which is this group, and Friedel-Crafts alkylation places alkyl group on a benzene ring. So this is what happened in a Friedel-Crafts reaction. Benzene ring reacted with acyl chloride in the presence of aluminum chloride, Lewis acid catalyst, and then in the second step when you add water, we will see that the acyl group, this yellow colored group, is added to the benzene ring. And acid anhydride, normally used as the source for the acyl group. Okay, acid anhydride, so this part, and then this would be your leaving group. Here would be the chloride, but here this is ester part would be going to be your leaving group. You can use acid anhydride with a benzene ring in the presence of Lewis acid catalyst, aluminum chloride and water. Then you will add acyl group on the benzene ring. Okay, and then from this part, I told it's the ester, but no, it's going to be a carboxylic acid. Okay, so you will be generating a carboxylic acid because this is alkyl carbonyl oxygen. This will grab a hydrogen and making acid. Acyl chloride or an acid anhydride is a source of the acyl group. So you can use any of those. Lewis acid, aluminum chloride is required for reaction to take place. So here's the mechanism. And this will show you how to generate the acylium ion. Okay, so once you form the electrophile, which is going to be alkyl group and a carbonyl group. Now this carbon, you can see only 3 bonds on carbon. It's a carbocation. It's a positively charged carbon, electron deficient. So the benzene ring, electron rich, attacks the carbon, carbocation. And so this carbon will become positively charged, which is the same mechanism as we learned in the previous session. And then the base grab the hydrogen and reform the benzene ring. Electrophile adds to the benzene ring. Base in the reaction mixture removes the proton from the carbon that form the bond with the electrophile. And let's see how we can generate the electrophile. Now this is the acyl chloride and our Lewis acid catalyst is aluminum chloride. Remember the Lewis acid base definition. Lewis acid is a species that is electron deficient. So aluminum with 3 chlorine on it has only 6 electrons. So it is electron deficient. So aluminum is Lewis acid. Chlorine has lone electron pairs. Okay, so this can act as a Lewis base. Okay, so this is going to give its one of the lone pairs to the aluminum and form a bond. Now that makes, now the aluminum has 4 bonds. That will give aluminum formal charge -1 and chlorine would be positively charged. So now when this happened, so the carbon chlorine excuse me, bond breaks and generate acylium ion. And this is the electrophile needed for the Friedel-Crafts acylation plus AlCl4 minus. Acylium, so this ion is, instead of a carbocation, the better name for this one is acylium ion is the electrophile. Okay. Aluminum chloride react with the product of Friedel-Crafts acylation. Now let's see, we used aluminum chloride for this reaction to take place. Once the acyl group is on the benzene ring, aluminum chloride, remember we talked that it is a Lewis acid, and here you have a Lewis base having lone pairs on oxygen. So there is a Lewis acid base reaction take place, so the aluminum chloride will form a bond with the oxygen. Okay, so because of that, normally more than one equivalent of aluminum chloride must be used in a Friedel-Crafts acylation. If you use 1:1 ratio, one aluminum chloride will help you to get to the acylated benzene ring, but another one will go and sit next to the oxygen, forming a Lewis acid base complex. So then we will end up having more of the benzene rings to be acylated, but we will not have enough of these. Okay, so as a result, normally we need to use more than one equivalent of aluminum chloride in order to have a complete reaction. Aluminum chloride forms a complex with the carbonyl group in the product, like here, and then water is added to liberate the product from the complex. So the final product will be removed, released or separated from this complex by adding water. Okay, so now you have the acylated benzene ring. And here's another reaction. If you want to add a formyl group is a carbonyl group with hydrogen coming from the formic acid, or you can say formyl chloride. Okay, benzaldehyde cannot be made. So this is benzaldehyde. Cannot be made by Friedel-Crafts acylation because the needed acyl chloride, which is the formyl chloride, is unstable. Now you can have acetyl chloride having CH3 here, which is going to be acetyl chloride, but with one carbon. This is formyl chloride. Remember, if you have a OH group here, that would be your formic acid with one carbon. So this is formyl chloride, which is unstable. So what we're going to do is we have to make the formyl chloride in the reaction mixture. We call it as an in situ formation of the reagent. With carbon monoxide and hydrochloric acid under very high pressure, we can form the formyl chloride. And then you add catalyst aluminum chloride and copper chloride, both of these catalysts, along with benzene ring, so we can make the benzaldehyde. Okay. So that is the Friedel-Crafts acylation. Remember, the acylation is adding a carbonyl group with alkyl group. Okay, and the Friedel-Crafts alkylation is you're adding an alkyl group. For this also you need to have the Lewis acid aluminum chloride. And this is the mechanism. Generating the electrophile alkyl halide similar to acylation. Chloride, Lewis base, Lewis acid, complex form. And then it removes this whole complex. This alkyl group and chloride bond will become weakened. So then, since the 2 electrons on the bond gives to the chlorine, alkyl group will end up having a positive charge, which is a carbocation. And that is the electrophile needed for the Friedel-Crafts alkylation. And then it takes the same form of mechanism. Benzene ring attacks the carbocation, and then the base takes a proton and regenerate the benzene aromaticity. Alkylated benzene product is more reactive than benzene. Now when you add an alkyl group onto the benzene ring, now it is an alkyl benzene compound, which is going to be more reactive than the benzene. Therefore, a large excess of benzene is needed to avoid multiple alkylations of the ring. Okay, so we have to add more of the benzene, so that way we can minimize having more alkyl group adds on to the same benzene ring. Now sometimes when you try to do alkylation, there is a possibility that the carbocation rearrangement can take place. For example, let's say you use this benzene, we take excess amount for the reason that we talked, and we want to add this alkyl group. How many carbons we have? 1, 2, 3, 4 carbons, butyl chloride with aluminum chloride. Okay, and what we want to add, let's say we want to add this butyl group. So if it is not rearranged, so this should be the product we should be getting, unrearranged alkyl substituent. But along with this, maybe you see here 60 to 80% we get rearranged alkyl substituent, maybe about 20% of, or less than 20% would be of this compound. Okay, so how do we get the rearrangement? You see here we saw in the previous slide how the carbocation, alkyl carbocation forms. It's a primary carbocation. Primary carbocations, we know that they are not stable. Okay, so once the primary carbocation forms, if there is a possibility it can form a secondary carbocation, it would do that. So the hydrogen will move on to this carbon and will create a secondary carbocation. So that is what is going to add on to the benzene ring. And now this is tertiary. We have a tertiary butyl group, but here CH2Cl. So this carbon is going to be primary once the chloride is lost. Okay, so then we would expect a chloride will leave and then you generate the primary carbocation. If that is the one that is going to react with the benzene ring, this is the corresponding product. But it is only 0%. It's only 0%. Okay, which is the unrearranged alkyl substituent. But the 100% of the rearranged alkyl substituent is attached to the benzene ring. Okay, how does the rearrangement takes place? So this is your primary carbocation. Now it is a methyl shift. Methyl group will shift onto this carbon, generating a tertiary carbocation. Now this will add on to the benzene ring. Should we draw primary carbocations? Remember we learned in organic 1, primary carbocations are not stable. Okay, Friedel-Crafts alkylation mechanisms are written as if a primary carbocation is formed, although we know that primary carbocations are too unstable to be formed. So what's happening is it's not going to even form as a stable compound during the process of the formation of the Lewis acid base complex. The rearrangement takes place. Remember the chlorine lone pair form a bond with the aluminum. So this is what's happening, right? So this is the molecule as it is. So there is a bond between this carbon and chlorine, and bond between chlorine and aluminum group. Okay, so if it completely form AlCl4 minus complex, this should be the primary carbocation. So instead of making that complete breaking of AlClO4 minus, once this complex is being formed, this carbon carry a partial positive charge. And during this time, the hydrogen, adjacent hydrogen, will shift to this carbon. Okay, and then that generates secondary carbocation. Okay, so since this hydrogen moves to this carbon, the chlorine and the carbon bond breaks, and chlorine going to form a bond with this secondary carbocation. Okay, since the complete bonds are not being formed yet, we can represent them as a delta positive. So delta positive here, you're going to form a bond here. So now you have another delta positive charge on the secondary carbon. Bond with the chlorine, aluminum is partially negative. This delta sign represents partial negative, partial positive. And you call it as an incipient secondary carbocation. So a primary carbocation is never formed. So this primary carbocation never formed. Instead, through this process that we are showing you with the arrows, incipient carbocation is formed, which is this one, secondary carbocation. Okay, and then that is what going to adds on to the benzene ring. So always look for the carbocation rearrangement when you are doing alkyl substituents on benzene ring under Friedel-Crafts alkylation. So here's an example of a biological Friedel-Crafts alkylation. Biosynthesis of vitamin KH2. So this is your benzene ring. You can see here there is a carbocation formed. So the benzene ring with the lone pair adds on to this carbocation. Okay, so and then the base will grab the hydrogen and reform the benzene ring. And after the several steps, we can see vitamin KH2 is being formed. Okay. Putting a straight chain alkyl group on a benzene ring. So we saw that we had a problem. If you want to put a straight chain, that there is a possibility carbocation can rearrange. But if you really want to put that, how are we going to achieve that? So that's what we're going to look at now. Now, let's say you want to put 1, 2, 3 carbons chain propyl group. So what we can do is we can add the group as a acyl substitution. This is 1, 2, 3 propanoyl chloride. Okay, acyl group with aluminum chloride and water. The second step is the water with aluminum chloride. You can add this acyl group, acyl substitute benzene. And then the next step is we don't want to keep the carbonyl group. Instead, we want to make it CH2. We can use a reducing agent to reduce the carbonyl group to CH2 group. Remember, we learned about the oxidation and the reduction. Reduction is gaining of electrons. So the oxygen is more electronegative. So carbon is now electron deficient. Okay, by having hydrogen, carbon is going to reduce, going to have more electron density on carbon with hydrogen compared to carbon with the oxygen. We talked about that earlier, right? So we can achieve that reduction with hydrogen and palladium carbon. So we can add the propyl group. If you don't use this process or this method, what's going to happen? We will have a substituted benzene ring with a rearranged alkyl group. Remember, we saw this one here like this, right? So the primary carbocation will rearrange to secondary carbocation. So that will not happen when you try to do your synthesis like this. Add the correct number of carbons with the Friedel-Crafts acylation reaction. Reduce the carbonyl group to a methylene group. Catalytic hydrogenation reduces only a carbonyl group adjacent to a benzene ring. So the catalytic hydrogenation, it will not reduce the benzene ring, but it will only reduce the carbonyl group next to the benzene ring. Okay, but remember, we learn when we study alkene chemistry in specifically organic 1, and we also touch some of these reactions in organic 2 also. A double bond can be reduced or add hydrogens across a double bond using catalytic hydrogenation. So then the double bond will double bond, hydrogen will be added on to the double bond. But since benzene is different than being an isolated alkene, nothing can happen with hydrogenation, with catalytic hydrogenation to the benzene ring. Okay. Another way that we can reduce a carbonyl group is using Wolff-Kishner reduction. So for the Wolff-Kishner reduction, we use hydrazine, NH2NH2. Hydrazine, in the presence of a base, when you heat it, you can convert the carbonyl group into a CH2 group. Okay, and let's see the mechanism of that one. Okay, so the carbonyl group, you react with hydrazine, NH2NH2. Okay, and Remember, when we talk about the carbonyl chemistry, we learn how to form an imine. Imine is a primary amine with an alkyl group. Now you can consider this also as a primary amine because there are 2 hydrogen and an NH2 group. So imine is basically you form instead of oxygen, now the nitrogen will come to this place and form a double bond. So that is what you are seeing over here, formation of an imine. Since you have a NH2 here, instead of a methyl or any other alkyl group, there is a special name, we call it as a hydrazone, but it is a form of an imine. Okay, so you know how the mechanism works. Carbon, nitrogen, double bond formed, and then the nitrogen will end up having a NH2 group. Okay, NH2. So this is the hydrazone. And for this mechanism, we also need a base. So once a hydrazone is formed, what's going to happen? Hydroxide ion will remove a proton from this nitrogen and form this intermediate, nitrogen with a negative charge and 2 lone pairs. Now, this one can be resonance stabilized. Always, when you have a double bond, and then on the next atom you have a lone pair, there is a possibility that this can undergo resonance. Okay, so the lone pair on the nitrogen can come between these 2 nitrogen pi bond breaks, and then the lone pair goes to the double bond electron goes to the carbon as a lone pair. Okay, that is a delocalization of the negatively charged. So instead of negative charge on the nitrogen, now we find it on carbon. Now what happened? Carbon having a negative charge, carbon goes and find a proton from water molecule. Okay, so then this carbon will get protonated, right? So you have your OH minus and this carbon, now we have your hydrogen. Now this is the product we get from this protonation. Now what's going to happen next? So now we are still in the basic medium hydroxide. OH minus gonna go ahead and grab this second hydrogen on this NH2 group and gives its electron to this nitrogen. Okay, let's see what's going to happen now. The lone pair on this nitrogen forms another bond with this nitrogen. So it had 2 bonds here, now going to form another bond, a triple bond. And then the nitrogen carbon bond breaks, gives its electron to this carbon. And you are familiar with the nitrogen Lewis structure, right? There is a triple bond between the 2 nitrogen and carrying 1 lone pair on each nitrogen. That is what creates the nitrogen molecule, which is also a gas, very stable, small gaseous molecule. Especially if a reaction involves a removal of a stable, small gaseous molecule, that reaction will move forward. That is the driving force of the reaction towards the product formation. Just like the decarboxylation, removal of a carbon dioxide molecule, here removal of the nitrogen molecule is the driving force of formation of this carbon ion. And then this carbon ion will grab a hydrogen and complete the saturation of this carbon, giving you RCH2R. And that is the mechanism for the Wolff-Kishner reduction, where we use NH2 hydrazine, hydroxide and heating to reduce a carbonyl group into a CH2 group. Beautiful mechanism, isn't it? It's a different one. You haven't seen anything like this before. So it's a nice one. I like it, right? I hope you like it too. The ketone forms a hydrazone following the mechanism for imine formation. Okay, hydroxide ion remove a proton from the NH2 group. Reprotonation occurs at the carbon. Another deprotonation, loss of nitrogen, and reprotonation forms the product. Okay, that's what we talked about over here. Okay. Coupling reactions can put a straight chain alkyl group on a benzene ring. Now we know that there is a challenge to put a straight chain alkyl group on the benzene due to the rearrangement. Another way we can achieve that is using a coupling reaction. Coupling reactions are normally studied under organometallic compounds. Remember, we learned about the organocuparates, which is also a kind of a coupling type of a reaction. Okay, so there are several of these reactions. This is called Suzuki reaction. So what do we use for the Suzuki reaction? You use your chlorobenzene. It's not just the benzene. You have to use some kind of a halobenzene, halogenated benzene. And then we use the organometallic compound containing the alkyl group that you want to add onto the benzene ring. Okay, so for the Suzuki coupling you use boron as your nonmetal, and then you have two alkoxy groups and the alkyl group, and then you use the catalyst as palladium L2. Here L represent a ligand. Ligands could be some coordinating atoms or coordinating compounds that adds on to the palladium. We don't need to talk too much about it. Just remember L is a ligand. I hope you have studied about the ligands in Chem 2. Remember we learned about ethylene diamine is a ligand, and ethylene diamine EDTA is a ligand, and then we also talk about water can be a ligand, OH could be another ligand, I mean NH2 group could be a ligand, NO2 group could be a ligand, and oxalic acid, it's a bidentate ligand. Remember we learned those things. So the L represent those ligands. Don't worry too much about it, but just know the reaction. So what happens is when you add these conditions with the halogenated benzene, it would substitute the alkyl group to the chlorine. So we will have directly alkylated benzene ring. Okay, now we know three ways that we can achieve the unrearranged alkyl group on benzene. One way is this Suzuki coupling. The other way is you add an acyl group, and then acyl group can be reduced by doing a catalytic hydrogenation or Wolff-Kishner reaction. Basically two methods, but one of the methods have two ways to reduce the carbonyl group. That's what I meant. Okay. Okay, so you can achieve the same thing with organocuparate. Remember we know what is organocuparates. So the copper, lithium, so cuparate because we have the copper. So we use the cuparate carrying the alkyl group that we want to add. In fact, we know how to make the cuparate, right? Using this alkyl halide and then the copper lithium compound we learned when we studied organometallic compounds, I believe in chapter 10, right? Okay, anyways, so you use these two compounds, or the bromine will be substituted with this alkyl group that we want to add. Okay. Okay, so we'll stop here and then we'll start the next session in the next time.